Okay. Apart from the Java collection frameworks, there are many other third-party libraries support different kinds of implementations, such as Guava 12 Apache Collection Framework. And although these frameworks can support the similar or the same functionalities of these data types, their performance can have big difference. For example, Hassan performed an empirical study on the resource consumption of this container method call, and they surprisingly discovered that their energy consumption have the big difference. For example, if we perform the random access upon the linked list, we will find it will consume more energy than the array list. However, it is not easy for programmers to select the proper container types during the development. The reason is they are often unaware of how a container objects are manipulated because they only focus on the specific modules of the applications. And secondly, some of them are not familiar with different implementations provided by the different libraries. So they fear difficulties to find the best container types during their development context. So it is very crucial to find a way to assist them in finding proper container types. So in this paper, our aim is to synthesize such container replacement automatically for a given program so that the new program will consume less resources than the original one. And typically, the container replacement means that we need to find the container type for each container allocation statement, and also needs to find the proper method for each container method call. And as we all know, the computation can consume different kinds of resources, including the time, memory, CPU usage, energy, and so on. So without the loss of generality, we only want to focus on time cost in this paper, but we still expect our approach to be general enough to be easily extended so that we can also use our framework to reduce other kinds of resources. And according to our survey, there are two major lines of work. The first lines of work try to solve an optimization problem. Specifically, they enumerate the container types for each container allocation statement so that they can get many mutated programs. And then they will execute these programs with some test cases so they can monitor the resource consumption, such as the execution time. And finally, they will find the optimal replacement to reduce some kinds of resource consumption and get the optimized program. And the other lines of work try to solve a prediction problem. Similar to the first line of work, they also need to execute the program automatically to get some runtime information. For example, the number of the elements in the container objects. And then they will apply the pre-trained machine learning model or the predefined rules to this runtime information and get the strategy of the container replacement and generate the new program. However, these approaches are not sufficient to solve this problem thoroughly because of these three drawbacks. The first one is a huge overhead. As you can see, this approach have to execute the program multiple times with some test cases, especially for the first line of work, they have to mutate the program multiple times. So this can introduce a huge time consumption in the analysis. And secondly, they all demand the specific input to execute the program. So their replacement might be effective for some particular inputs rather than the general ones. So this can introduce the overfitting issue. And the second drawback is for some techniques. They may have very strong assumption that some container types are always exchangeable under any program context. But this assumption does not hold because, for example, the tree set is not always exchangeable with the hard set because the traversal upon these two kinds of container objects are totally different. So the program behavior equivalence cannot be ensured during the replacement. So in our work, we want to make sure that the new program and the original program satisfy two important constraints. The first one is a behavior equivalent, which means that the new program and the original program should return the same value for a given input. And here we only consider the input-output relationship and ignore other behaviors of the program. And secondly, we expect the new program to consume less time than the original one for sufficiently large input, and we call it as complexity superiority. So to achieve these two constraints, we need to actually set them as two critical goals for our synthesis algorithm. Actually, we need to answer two important questions to achieve these two critical goals. The first one is, which container types are exchangeable to ensure the behavior equivalence? And the second one is how to measure the performance of the container manipulating program so that we can determine whether the new program has the complexity superiority over the original one. So the answer to these two questions are very important to design our synthesis algorithm. And now I will illustrate how to handle these two issues and demonstrate our key ideas. For the first goal, let's come to see a simple example. In this program, we first insert two elements in these array list objects. And then we check whether this parameter has been inserted to this array list object before. So the value ownership, that is, whether this value is in this list, determines the return value of this function. So such functionality can also be supported by other container objects, such as a linked list, hash set, tree set, and so on. So we can notice that the exchangeable container types should achieve the original container usage intention, such as the value ownership in this example. To be more specific, the developers may use the containers because of two intentions. The first one is they want to query some container properties. And second one is they want to modify them. And now I will illustrate them one by one. Apart from the value ownership we mentioned in the example, developers may also concern about the index ownership, index value correlation, and the size of the container objects by invoking the corresponding container methods. And for more advanced container types, such as the linked hash map and tree map, they can also concern about the insertion order or the key order. And meanwhile, in order to query such container properties, they also need to update such properties at other program locations. For example, in this program, they actually need to modify the size, value ownership, and index value correlation of this array list object before the query of such value ownership. So according to these examples, we notice that when we invoke the container method, their semantics can be decomposed into two dimensions. The first one is the queries, and the second one is modifier. For example, the contents and the get method actually query the value ownership and index value correlation. And also, the add method of the hash set and array list actually modify the size, value ownership, and index value correlation in a specific manner. So if we want to achieve the original usage of the container, we actually need to make sure that the original container property queries can be supported. And also, such properties can also be modified in the same way as the original one. So in this example, we only concern about the value ownership. And also, the add method of this array list updates such property. And we notice that the hash set can also support the same query and modification. And although they have different effect on the size, but this property is not used in the program, so it has no impact on the program behavior. So we can just safely replace the array list with the hash set directly. So in this way, we can ensure the behavior equivalence. So to sum up, to achieve the first goal, we need to achieve the original usage intention of the container with some exchangeable container types. And to find such exchangeable container types, we need to support the original container property queries and modify such properties in the same way as original one. Okay, now I'm go to the second goal. Theoretically, we need to estimate the time complexity according to by utilizing the complexity analysis or the worst case execution time analysis. But this analysis are not practical for the real world programs, especially the ones using the advanced data structures. So we need to find some trade-off. And interestingly, we found that the programs before and after replacement only differ in terms of this container method call. So to determine the complexity superiority, we only need to determine the performance difference of this container method call. Technically, we introduce the cost model to describe the complexity specification of a container method. And this composed of two parts. The first one is the complexity classes. Actually, we divide the container method into different container classes according to their amortized time complexity. And for better formalization, we introduce these functions, complexity functions, to indicate such complexity class. But meanwhile, we notice some container methods still have the performance difference, even if they have the same complexity. So we still introduce the constant factor here. For example, the add method of the hash set is having weighted than the one of the array list. So we need to make sure that the constant factors should be larger than the one of the array list. So here we just show the example and set the concrete value of these constant factors here. But actually we will evaluate that as long as we preserve the specific order of such constant factors, the concrete value of these factors do not affect our synthesis result. So in this way, we can describe the performance difference in a fine-grained manner with the benefit of the complexity classes and this constant factor. So to determine the complexity superiority, we can introduce the container complexity superiority, just focus on the container method call. So we introduce this heuristic metric as the time cost of manipulating a given container objects. So come back to this example again, we can compute this heuristic metric in this way, and we found that the second one is smaller than the first one. So we know that the second one, we have the confidence that the second one is better than the first one in terms of the efficiency. So based on the above program abstraction, actually we can propose a synthesis algorithm Cres to achieve the original intention of the container usage so that the behavior equivalence can be ensured, and meanwhile, we can achieve the container complexity superiority so that we have opportunity to improve the program efficiency. So basically, our approach has this, the workflow of our approach is shown by this figure. And initially, it takes as input the thematic specification and complexity specifications as input. And these two kinds of specifications should be specified manually. And for each of stages, they were, I will demonstrate these three stages one by one. And for the first stage, we actually need the points to facts to identify which container method call manipulate a specific container object. So here we just utilize allocation-based abstraction to get to determine abstract container object. For example, for the allocation statement at line 2, it can determine an abstract array list object O2 here. So based on the sound points to analysis fact, we can find all the possible manipulations upon this object. So these are corresponding three container method calls. And then based on the thematic specification, we can obtain that the value ownership is queried for these container objects. And similarly, we can get the queried container properties for the object O11, that is the size, value ownership, and the index value correlation. So after the first stage, we actually get the set of the container properties queried upon each container object. And in the second stage, we can just utilize the result of the first stage because we can leverage the semantic specification and to try to find the methods can support the queried container properties and also modify them as the same way as the original one. So in this example, we can get such methods as candidates for these three container method call. So after the second stage, we have such sets for each container method call in the whole program. And the last stage is very actually straightforward because we can just enumerate the candidates and to calculate such heuristic metric and to find which one can induce the minimum value. So in this case, the hash set is the best. But here I want to emphasize that in some program, a single container method call might modify multiple abstract data type container objects. So in this way, we still need to ensure the type consistency. So we need to refine the enumeration based on the console example guided synthesis. So due to the time limitation, I will discuss this part in detail. So if you have interest in this part, you can refer to our paper. So this is the overall workflow of our approach. And lastly, I will demonstrate some theoretical results. Firstly, the new program P prime is behaviorally equivalent to the original one, as long as the points to fact are sound. And secondly, the new program has a container complexity superiority over the original one. And this is trivially held because, as we can see, the last stage of our algorithm can guarantee that this theorem must be held. And we also estimate the time complexity of our synthesis process. And given the points to fact, our synthesis process can be achieved in this time cost. So it's not very high. And here we just estimate this time complexity to show that our approach can be finished in the polynomial time as long as the points to set can be provided. So we do not give the very tight estimation of this time complexity. So we finally implement our algorithm as a tool named Cres. And basically it's established upon the pinpoint, which is a static analysis framework in Ant group. And particularly we use flow sensitive points to facts for the container property analysis so that we can collect all the queried container properties. And currently, our implementation supports the analyzing the containers in JCF, but as long as you provide the specification for other containers in other third-party libraries, we can also analyze and optimize them. We evaluate our approach from these three perspectives. Firstly, we select some these applications as the experimental subject of our approach. And as you can see, most of them are very fundamental infrastructures. So any efficiency improvement of these applications can benefit the projects established upon them. And as you can see, our approach can introduce about 8.1% speed up for these applications. And for some applications, this speed up can reach over 20%. So it's very meaningful results. And also we categorize synthesis replacement patterns. And apart from the ones we mentioned before, we also, Cres can also discover the synthesis, the replacement by replacing the tree map with the hash map if they found that we do not traverse this tree map or do not get any information about the keys. So we can use a lightweighted hash map directly. And we can generate 107 replacement here, and particularly 71 replacement have been accepted and confirmed by the developers. We also quantify the time and memory cost So as you can see, our approach can figure with the linear time complexity, linear scalability, and we also can finish the analyzing the project with about 400,000 lines of code in 14 minutes. And here I want to mention that this is just the I just try to show the scalability. It does not mean that our approach is has a linear time complexity. And in the evaluation, we also found some very interesting findings. The first one is the precision of the points to analysis can affect the result of the synthesis, because if we replace the flow in sensitive pointer analysis with the flow insensitive one, Cres can miss 33 replacement cases. So this is caused by the conservative result of the container property analysis. So Cres can miss these optimization opportunities. And lastly, I also want to mention that our approach is insensitive to the concrete setting of these constant factors, because as long as we can preserve this order when we set these concrete values of these constant factors, our approach can always give the same results. So we just randomly generate such constant factors as long as this order satisfied. But Cres also suffer from some drawbacks. The first one is, as you can see, the container complexity superiority does not imply the the complexity superiority, because actually we do not estimate the whole complexity of the complexity of the whole program. We just measure the container method calls, and this also this metric is heuristic, because some container method call may be executed multiple times, but we did not consider such frequency. So we still need the precise but also computable complexity guidance to for our synthesis process. And also, our approach is aware of some usage intention of the containers. Here is a real-world example. As we can see, this linked list is traversed in the second loop backwardly. So according to our approach, Cres can just replace this linked list with the array list so that it can support more efficient random access. But the optimal solution should be use the iterator, the reverse iterator, to replace this loop and this random access. But currently, our approach cannot identify this semantic usage of the container. So this can be the interesting future work. To conclude our approach, in this work, we propose a new program abstraction for the containers. Particularly, we propose the container properties to summarize the semantics of the container methods. And also, we define the cost model as the method complexity specification. And furthermore, we utilize these two kinds of specifications and propose an efficient and a sound synthesis algorithm, Cres, to ensure the behavior equivalence and also find the opportunity to improve the program efficiency. And that's all for our talk. If you have any questions, please feel free to propose. Thank you for listening.
Very nice work and very nice presentation.
Thank you.
Could you please switch back to slide 29?
29, okay.
29.
This
yes.
one? Yeah.
So lines 5 and 6.
So
it's checked that the container contains the value. In this case, the addition is needed. I think the previous slide shows it better.
Oh.
So in this case, I think the original containers are released, in which case the check on line 5 is necessary but expensive.
Yeah,
if you refactor it to hash set, you don't even need to have this check on line 5. Because it's always one element or 0, 1 elements in the set. So the point is that you can change it to a better program that doesn't perform the check on line 5 if you change arrays to, let's say, hash set for that purpose.
Yes, exactly. It's very.
Does it do that or you consider that?
Actually, we just try to optimize this problem under the specific syntax because as you can see, I just hide the type and method here. And actually, this is just a sketch of our synthesis. So for more insightful optimization or just to remove some checking or some statements, it might be possible. But currently, we just focus on the replacement in this form. So currently, we do not consider such kind of the synthesis problem.
Thank you.
Thank you for the question.
Do you know why people fairly frequently use the wrong container? Is it like laziness, convenience, or is it ignorance? Or was there, for example, an older version that was okay, and then they changed the code, they don't use a certain feature anymore, and they don't bother changing the collection? Have you looked into the reason why people get it wrong so often? Because I don't think about it the first year. You're supposed to know that as a programmer, I think.
Yeah, it's very interesting question. But actually, in our work, we have not delved into the details about these reasons. But I also interview some developers who often use Java programming because this is work collaborating with Ungroup, and most of their developers use the Java program. So they say that they just have some preference to use specific kind of the data types, containers. For example, if they use the Java collection framework, if they want to use a list, almost all of them will use arrays instead of the linked list or something like that. And also, if some third-party libraries are updated or some new libraries are imported, they will not go to see the details, the implementation details about this new implementation. So they tend to use the JCF only. But although there are some different implementation provided by other libraries, they will not go to see the real, what's the difference between these different implementations. So I think it's an interesting aspect that needs a further exploration, and I will try to think about it. Yeah, thank you for your question and suggestion.
Thanks for the talk. I was wondering about properties like thread safety when you're considering observational equivalents, maybe like a thread safe and a non-thread safe data structure with a observational equivalent in a single-threaded context, but not in a multi-threaded context. And have you thought at all about like integrating that kind of property into your analysis?
Yeah. Thank you. Thank you for your question. This is also a very interesting question. Because of time limit, I didn't show this in the main contest. Oh, sorry. I just show this in this way. Because we just provide a general framework to, for example, we can label the semantics of each container method, but actually we can extend this. We can extend the, for example, the properties we concern about. For example, the thread safety. And as we know, there are some existing works focused on this part. They want to ensure that after replacement, the program is still the thread safety. Yeah. But now we do not consider this part. But if you want to consider this feature, we can just extend a new properties here. For example, if we use thread safety, for example, the thread safety container types, we can check whether there is a container method call using threads and manipulate these container objects. If so, we need to ensure the thread safety. Otherwise, we do not need such advanced feature. So as the future work, it's possible to define more properties, and as long as you provide such utilize the properties to label the message semantic specification, we can extend our frameworks further. So it can be the improvement of our approach. Yeah, thank you for your question.
Yeah, thank you, speaker.